Welcome to this explainer. Have you ever found yourself just yelling at your computer because it absolutely wouldn't do what you wanted it to do? Well, we've all been there for sure. But the real truth is, computers just don't speak our language. They don't have that innate human intuition. They actually require a completely different way of thinking entirely. So today, we're going on a journey, the translator's journey. We're going to explore the core challenge of bridging the massive gap between our messy, natural human intelligence and the highly literal, step-by-step logic of a computer.
Think about it. On one side, we have our human intention. That's the problem we want to solve. On the other side, we have the solution that a machine can actually execute. And that gap in the middle? Well, that's us. Because computers literally lack our natural intuition and intelligence, they can't just figure things out on the fly. This means we have to step in and act as the translators. We have to take our abstract goals and convert them into a highly careful thought process with meticulous planning. We literally have to connect the pieces for them.
So here is our roadmap for today's explainer. We'll be looking at thinking like a computer, the top-down approach, algorithms, flowcharts, pseudocode, and finally, making decisions and looping.
All right, let's jump straight into Section 1, thinking like a computer and finding efficient logic.
There is a huge contrast between the human brain, creative, scattered, constantly firing off a million brilliant intuitive ideas at once, and the linear logic required for a machine. A computer just cannot process that scattered human creativity. To get to an efficient solution to a really complex problem, we actually have to straighten out that tangled human thought process into a single, linear, step-by-step wire. We have to feed the computer instructions in a perfectly logical sequence, and honestly, doing that is what ultimately saves us time and avoids a ton of frustrating bugs down the line.
Moving right along to Section 2, the top-down approach, or just simply breaking it down.
You absolutely cannot just feed a massive, complex problem to a computer all at once. It will choke. Seriously, it just won't work. So you have to use what's called a top-down approach. You take your big, scary problem and you successively break it down into smaller and smaller subproblems. You basically just keep slicing it up until each little piece is so simple, it's easily solvable completely on its own.
Let's look at how this actually works in practice with a classic academic example. Say your overarching problem is to compute the average marks of a student. Now, to a computer, an average isn't a natural, intuitive concept. So we break it down into two much smaller subproblems. First, we tell it to compute the sum by adding all the individual grades together. Second, we tell it to compute the average by dividing that sum by the number of subjects. See? One large task is suddenly just two smaller, highly manageable tasks stacked right on top of each other.
Which brings us to Section 3, algorithms, those crucial stepwise processes.
Now, I really want you to think about this question for a second. How do you prepare a cup of tea? It seems ridiculously simple, right? You'd probably just do it on autopilot every morning. But if you had to explain it to a literal robot that had never even seen a kitchen before, suddenly the hidden, step-by-step complexity of this incredibly mundane daily task becomes extremely obvious. To teach a computer to make that cup of tea, you have to create an algorithm, which is just a finite number of sequential steps. Step 1, if the kettle is empty, fill it. Step 2, plug it in and switch it on. Step 3, empty the teapot and place the tea leaves inside. Step 4, if the water isn't boiling yet, go back to Step 2 and wait. Step 5, switch off the kettle. Step 6, pour the water into the teapot. By walking through this funny little metaphor, we totally demystify algorithmic thinking. It's really not magic. It is literally just a highly structured version of your everyday logic.
But you can't just throw any random list of instructions at a machine and call it an algorithm. It has to follow strict rules. It requires precision, meaning every single step must be perfectly defined. Uniqueness, where the result of each step depends only on the input and the preceding steps. Finiteness, and this is a really big one. The algorithm absolutely must eventually stop. An infinite loop is a programmer's worst nightmare. It also needs to take an input, produce an output, and ideally possess generality, meaning it can apply to a broad set of inputs, not just one highly specific scenario.
All right, Section 4, flowcharts. Let's get into pictorial logic. Flowcharts are basically a universal visual map. They translate our algorithm into a crystal clear flow of communication using very standard symbols. Think of an oval as the terminal, the hard start or end of your program. A rectangle is for processing, like doing math or moving data around. The diamond is super important. It denotes a decision where the path branches based on a simple yes or no question. The parallelogram shows input or output, and the arrows, the flow lines, show the exact sequence and direction of all our logic. And because we're translating our messy human thoughts into strict computer logic, our flowcharts must follow firm design guidelines. They have to be neat and clear, with a very logical start and finish point. You can only have one flow line coming out of a processing rectangle. However, multiple lines can totally leave a decision diamond depending on the different answers. And whatever you do, please avoid intersecting flow lines. You never want to cross the streams. Keeping it clean makes testing and debugging an absolute breeze.
Next up is Section 5, Pseudocode, the beauty of plain English logic. To put it perfectly, pseudocode is a generic way of describing the algorithm without needing any specific programming language notations. It literally just uses plain English. And this is brilliant because it makes your logic compact, highly readable, and so much easier to modify than trying to redraw an entire visual flowchart from scratch.
We use capitalized, punchy command words like read for input, print for output, compute for math, set to initialize a value, or increment for a counter. Doing this simulates the exact feeling of writing actual code, but because it's still just plain English, anyone on your team can read it, understand the logic instantly, and verify that the translation from human thought to machine instruction is flawless.
Finally, we hit Section 6, making decisions and looping. These are the core mechanisms of logic.
Here's where we look at the direct contrast between the two core mechanisms of logic. We have selection, which is all about making choices. This uses if and else statements to look at a condition and actively branch down one of two specific routes. And then we have looping, which is all about repeating actions. This uses while or for statements. I mean, why waste your time writing the exact same set of instructions over and over again? Looping lets the computer efficiently repeat an action automatically until that desired output is finally obtained.
So here is exactly what that selection logic looks like in pseudocode syntax. It reads, if a certain condition is met, then execute statement 0. Else, if it's not met, execute statement 1, and then end if. It is perfectly, ruthlessly binary. This is exactly how a computer makes a firm decision based on the carefully translated logic we provided for it.
And for a loop, it's all about the while statement. While a specific condition remains true, then keep executing statement 1. And while, the very second that condition becomes false, the loop stops entirely. This right here is the absolute secret to a computer's incredible speed and power. It saves massive amounts of time and effort by iterating through vast oceans of data automatically, all based on this one simple structure. So, we've gone all the way from the messy, brilliant human brain right down to precise loops and binary decisions. You now understand the translator's journey. So I want to leave you with this final provocative thought. Take a look around your life today. What daily task could you write an algorithm for next? Start breaking your world down into subproblems, and I bet you'll find you're already thinking like a computer. Thanks so much for joining me on this explainer, and keep exploring.